In this talk, we present a global feature-based partial-to-partial point cloud registration approach. Existed algorithms can be divided into two categories. One is correspondence matching-based method, which first extracts point-wise features from input point clouds, and then they are used to calculate the match matrix. Finally, weighted SVD is applied to obtain the 3D rigid transformation. However, the features are only extracted from local geometry, leaving the others untouched. Besides, accurate matching requires distinctive geometric structures, resulting in a limited number of matches or poor distributions. The other is global feature-based method, which aggregates global features from entire point clouds. Then, they are fed into a network to regress the 3D rigid transformation. Although they can utilize the global information, they ignore the negative effect of non-overlapping regions, which further interfere with the regression process. We propose an iterative approach to reject non-overlapping region by learning overlapping masks. First, at each iteration a 5-layer MLP is adopted to extract point-wise features of the input, which are weighted by the previously predicted overlapping masks avoid the influence of outliers. Then, features are aggregated by max pooling and information of two inputs are exchanged by skip links. Moreover, a 3-layer MLP is applied to generate the global features. Here, the information interaction promotes the partiality Pepsian ability. Given the global features, there are two tasks left in the pipeline. One is overlapping mask prediction process. The other is 3D transformation regression process, which predicts the 3D quaternion and translation with enhanced features from the mask prediction branches. Based on the previous outputs, mask prediction becomes more precise. Meanwhile, by avoiding the negative effect of outliers, the regression process can also benefit from the overlapping mocks. Here is the entire pipeline of OMNet method. Here we also find two problems associated with ModelNet 40 dataset. First is that previous methods generate the point clouds by sampling only once on their CAD models, which means points in the source have exact correspondences in the reference. Training on this data leads to an overfitting issue. Second is that there are 8 axisymmetrical categories, which means it is reasonable to obtain arbitrary angles on z-axis. Thus, we argue that the reference point cloud should not be copied from the source point cloud, and we adopt the twice sampling strategy, where the 2 point clouds are sampled independently from the same CAD model. For the axisymmetrical categories, we simply remove them. We further demonstrate these two problems by training on these 8 categories, and only generate rotations around z-axis. The result shows that all 4 methods become relatively worse transferred from OS to TS data. As a result, OS incurs overfitting, WIC and TS not. We train our network with 2 losses. One is regression loss, where we use the combination of L1 and L2 loss. Second is overlapping mask prediction loss, where we adopt the frequency-weighted classification loss. Here shows our experiments. We compare our method with several existed traditional and deep learning-based methods on the OS and TS data of ModelNet 40 benchmark. We evaluate on 4 scenes including unseen shapes, unseen categories, Gaussian noise and different partial manner. It can be easily found that our method outperforms all the other methods on every metric, except 2 cases, as shown in blue boxes. To demonstrate the robustness of our method, we further evaluate on the data with different level Gaussian noise and overlapping ratios. As shown in the figures, our method is robust to noise and performs better in lower overlapping cases. We also visualize the intermediate results. From top to bottom there are registration results, errors between global features and predicted masks respectively, and the final column shows the complete process. As shown in ablation studies, each component improves the performance. By controlling the number of overlapping points, we find that using all of them is better. And better result can be achieved by setting larger factor between the quaternion and translation. Here are some qualitative results on ModelNet 40 benchmark, and it's obvious that our results are closer to the ground truth. To summarize, we propose a global feature-based registration network OMNet, which is robust to noise and different partial manners by learning masks to reject non-overlapping regions. We expose an overfitting issue and axisymmetrical categories of ModelNet 40 dataset and propose a more suitable data generation method. We provide qualitative and quantitative comparisons with other works on several scenes, showing state-of-the-art performance. Thank you.